This is Goddess of Science Physics, and I'm Mrs. Bolvin. Today, in part 5 of Newton's First Law series, we're going to talk about mass and inertia. Woo! So exciting. So, mass is the amount of inertia an object has. Um, so, mass is actually a measure of inertia, the amount of matter that's present in an object. So, you probably knew mass is the amount of matter present in an object, but you didn't know how it was linked to inertia. So the amount of inertia an object has depends on its mass. So the more matter present, the more it's going to resist a change in its state of motion. For example, if you have a large side-by-side French door refrigerator that is empty and you try to push it across the floor, it has a certain mass. It's going to take a certain amount of force to get it to move. But if you fill that up with gold bullion or gold bars, that's going to have a much greater mass and it's going to take a lot more force to get it to move. So it has more inertia because it has more mass. Okay, so mass is the measure of inertia of an object. Okay, so put those two things kind of equal in your head. So a lot of times when I teach physics, people get mass and volume confused. Don't confuse them. Volume is all about the space. Mass is all about the stuff that makes up an object. So volume is the measure of the space taken up, and it's usually measured in units such as cubic centimeters, cubic meters, milliliters, liters. All those are units of volume. Has nothing to do with mass. Mass is measured in kilograms in physics class most of the time. So mass is also not weight. It's so often confused, and the things that measure those two things are often confused as well. So mass is the measure of the amount of material that makes up an object. Weight, as you remember from earlier in the year, was the measure of gravitational force acting on the object. So if we have a stone and we mass that stone here on Earth, and then we take it to the moon and mass it again, it's going to have exactly the same amount of material because that stone, provided that nothing's happened to it from here to the moon, it's going to have exactly the same mass because it's going to have exactly the same amount of material that's making it up. So mass of an object is equal in all locations. It's not dependent upon where you are, what planet you're on, because it's the amount of matter that's present. Weight, however, is another story. So it can vary on different places on the Earth. It's going to be much less on the moon or in other places in outer space because it's the measure of the pull of gravity on something. So here's a kind of an interesting thing to think about. It's just as difficult to shake a stone in its weightless state in space as it is on Earth because the stone is made up of particles, and to move it you have to have a certain amount of force. So you're going to have that same amount of force in space as you do on the Earth because it's still made up of the same amount of stuff. Okay, so mass and weight, their relationship, and just wanted to stop and talk about what we're using to represent weight. W doesn't really do it for me because the same way as we used A with a little sub g for acceleration due to gravity because it's a special kind of acceleration, weight is still a force, so it's a special kind of force. So an F, capital F, and a little g, the force due to gravity. So mass and weight are proportional to each other in a given place. They are never, no, they aren't equal to each other. Whoa, this is a lot of stuff here. Okay, let's attack this one line at a time. So 1 kilogram weighs 9.81 newtons. Newton is the unit used for forces. I'm going to use newtons a lot. So mass is measured in kilograms. You know that. The SI, or the metric unit of force, is a newton, and because it's named after old Sir Isaac Newton, that is, we're going to use a capital N to represent that that's the unit. So if you say 10 with an N after it, capital N after, it's 10 newtons. So 1 newton is 1 kilogram times a meter divided by seconds squared. That seems like really awkward, so can you imagine why they came up with the name Newton? And, you know, hey, he was kind of a big deal in his time, and still today. We're still studying him. So we're going to use, instead of saying this all out, we're just going to use Newton. It's much easier. The American system, of course, has something different. We use the unit pounds to describe force. When you step on the scale, it's measuring your weight, or the force due to gravity, and it's measured in pounds here in America. At the Earth's surface, 1 kilogram is about 2.2 pounds in weight, and it's also about 9.81 newtons. So all of those are kind of equal to each other on the surface of the Earth. So here's the formula to find the weight of something. So I like to call this the FMA formula. So force is a big F equals mass times the acceleration due to gravity wherever you are. Usually, unless I tell you differently, you're going to assume that you're on the Earth, and the acceleration due to gravity on the Earth is going to be 9.81 meters per second squared. The other way that you can write it to show that it is in fact a weight, you got the force due to gravity, F sub g, equals the mass times the acceleration due to gravity. Either one is fine. You just have to realize that weight is actually a force. Let me say that again. Weight is actually a force. Okay, weight is a force. There, I said it 3 times. People will be like, I can't understand how to find weight. We don't have a formula for that. Yeah, we do. It's right here. This is our formula for weight, right here. It's awesome. Okay, that's it for this time. Thanks for joining me. Have a great day.